Hello and welcome to The Space Above Us, Episode 119, Space Shuttle Flight 47, STS-49, Rendezvous and Rescue. Last time, we took a little diversion with a shorter episode, which will allow this episode to be anywhere near a reasonable length. We met 24 new spacefarers, hailing from 5 different countries, with one of those spacefarers tipping the scales at around 100,000 kilograms. That one would be Space Shuttle Endeavour, who we welcomed to the orbiter fleet, returning us to 4 operational orbiters. And we also set the stage for today's episode by introducing an unlucky spacecraft known as Intelsat 6F3. Today we'll be talking about STS-49, the first flight of Space Shuttle Endeavour. You might think that with a brand new orbiter, they might want to take it nice and easy with this mission, but you would be wrong. No, today we have one of the craziest shuttle missions I've ever read about. We're going to perform the first ever hybrid orbital rendezvous. We're going to capture a satellite not designed to be captured. We're going to slap a new rocket onto it before letting it go. And since we still haven't had enough, we're then going to try a series of EVA experiments that will help build the space station. Let's just get right into it. Whether it was because this was the first flight of a new orbiter, because the flight was so jam-packed with stuff to get done, or a combination of both, this flight is made up almost entirely of spaceflight veterans. So let's meet our unusually familiar crew. Commanding the flight was Dan Brandenstein. We last saw Brandenstein commanding another mission featuring a tricky rendezvous, the retrieval of the Long-Duration Exposure Facility. For the last 5 years, Brandenstein has been chief of the astronaut office, wielding great influence on which astronauts flew on which missions. With this being his last of 4 flights, maybe he gave himself a nice little going-away present, a chance to really put his rendezvous skills to the test. Joining Brandenstein up front is our lone rookie for this mission, Kevin Chilton, or Chili to his friends. Kevin Chilton was born on November 3rd, 1954 in Los Angeles, California. He graduated from the U.S. Air Force Academy and somehow earned a master's degree in mechanical engineering from Columbia University the very next year. After that, he learned how to fly, slicing through the skies of Japan, Korea, and the Philippines in an RF-4 Phantom II. He next learned how to fly the F-15 and returned to Japan before coming home to cycle through a number of leadership roles and graduating from test pilot school. He was conducting weapons and systems tests for the F-15 and F-4 at Eglin Air Force Base in Florida when NASA came calling in 1987. This is his first of 3 flights, and after his NASA career, he'll return to his Air Force career, eventually rising to the rank of 4-star general. Moving back in the flight deck, we find Mission Specialist 1, Rick Heeb. And a minor correction from last time he joined the show, his last name is spelled H-I-E-B, which is pronounced Heeb, not Hybe, which is what I said the last time we saw him fly on STS-39, which deployed and retrieved the SPAS platform among other objectives. The flight was called the most complex deploy and retrieval mission of the entire shuttle program, with dozens of rendezvous maneuvers being performed. Heeb's selection for both that mission and this one makes sense because before becoming an astronaut, he worked as one of the rendezvous flight controllers. In fact, he wrote a piece of software which will prove critical to how this flight unfolded, and would eventually evolve into RPOP, Rendezvous Assistance Software that is still used in space to this day. For this flight, he'll be heading outside to help capture Intelsat. This is his second of 3 flights. Moving to the left, we find Mission Specialist 2, Bruce Melnick. We last saw Melnick flying as MS-1 on STS-41, which deployed the Ulysses space probe. Melnick is the only mission specialist not heading outside on this mission, but still has a critical role to play as the operator of the remote manipulator system during the Intelsat capture. This is his second and final flight. Heading downstairs, we find Mission Specialist 3, Pierre Thuot. Thuot is another pronunciation that I have to correct. His name is spelled T-H-U-O-T, so I went with Thuot, but nope, it's Thuot. Oh well. We last saw Thuot flying as MS-1 on STS-36, a classified flight that is notable for having the highest orbital inclination of any shuttle flight. Well, with this mission he'll grab the record in the other direction, since this flight has the lowest inclination of any shuttle mission. Thuot's job today will be the initial capture of Intelsat, so no pressure. Next on the middeck is Mission Specialist 4, Catherine Thornton, who sometimes went by KT. We last saw Thornton flying on STS-33, another classified DoD mission, making her the only woman to fly on a classified shuttle mission. I don't know what she did on her secret flight, but today she'll be heading outside to help test EVA techniques for the space station. This is her second of 4 flights. And rounding out the crew of 7 is Mission Specialist 5, Tom Akers. We last saw Akers flying alongside Melnick on STS-49, sending Ulysses out past Jupiter so that it could be put into a heliocentric polar orbit. He'll be joining Thornton outside testing EVA techniques on this, his second of 4 flights. If this seems like a really spacewalk-heavy mission to you, you are absolutely right. But there's a reason for that. Some plans for construction of the space station called for over 1,000 spacewalks, and while refinement of the design and procedures would cut that down to a much more reasonable couple hundred, the fact was that NASA was going to be spending an order of magnitude more time outside in the near future. It was time to start pushing the limits a bit to see what crews could handle. With that in mind, this is the first shuttle mission with 3 scheduled EVAs, and they were purposely scheduled on 3 consecutive days. Space Shuttle Endeavour arrived at the Kennedy Space Center for final outfitting and checkouts on May 7, 1991. Exactly 1 year later, it was on Launch Pad 39B, fueled and ready to go, if the weather would just clear up. As is all too familiar, the local weather in Florida was a little too iffy for a landing after a return to launch site abort, and even the weather across the Atlantic at the emergency landing sites was not cooperating. Throw in some minor technical issues and a wayward airplane entering the launch keep-out area, and it seemed that Endeavour had 1 more day to wait. But after a brief delay of 34 minutes, the weather cleared, the tech issues were resolved, and the plane was shooed away. At 7:40 p.m. Eastern Time on May 7, 1992, Endeavour roared off of the pad, finally healing a Challenger-shaped wound opened more than 6 years earlier. The ascent profile for STS-49 was slightly different than usual. The orbital inclination of the flight, that is, how tilted its orbit is with respect to the equator, was the lowest of the entire shuttle program, at 28.3 degrees. That's significant because Launch Complex 39B sits at 28.6 degrees latitude. Now, that might not sound like that big of a deal, since we've flown to 35 degrees, 57 degrees, and even 62 degrees. Who cares if we go down by 1/3 of a degree? The difference here is that all those other inclinations are greater than the latitude of the launch site. All you have to do is change your launch azimuth, the horizontal direction you fly when leaving the pad. But the lowest you can get by changing your azimuth is the same inclination as your launch site's latitude. So, rather than just tweaking the direction they were flying, Endeavour would have to sort of brute force change the inclination. One way to think about this is that typically when the shuttle lifts off and finishes rolling to its launch azimuth, its guidance computers don't see any major error in the trajectory. With STS-49, even if things went precisely perfectly, they were still going to see a 0.3 degree quote-unquote error that they needed to fix. I'm just going to leave this here, otherwise I'm going to go down a whole flight dynamics rabbit hole, and I already need to do that later in the episode. So just appreciate that the fact that Endeavour flying into a lower inclination is pretty neat. The rendezvous with Intelsat was scheduled for Flight Day 4, but work to make it happen began immediately. Rather than settling into orbit and then starting the approach, the OMS-2 burn, performed less than an hour after main engine shutdown, was targeted to start bringing Endeavour and Intelsat closer together, right off the bat. This would be the first hybrid rendezvous attempted in space. Typically in orbital rendezvous, you have a passive target spacecraft and an active chaser spacecraft. This generally makes things a lot simpler. Rendezvous are usually planned in a reference frame centered on the target spacecraft. Now, of course, that frame is moving. It's whizzing around the Earth at 17,500 miles per hour. But by looking at it in the right way, and by building the math in the right way, you can sort of treat it almost as if it's stationary, with only the chaser spacecraft moving. But if the target starts doing its own maneuvers, that frame is no longer stationary, which makes things complicated. Well, today, we're going to make things complicated. After Intelsat limped into orbit in 1990, it just kept going, raising its orbit to around 560 kilometers. The Intelsat operators were concerned about atmospheric drag pulling their orbit lower and lower, and they were also concerned about the effect of that atmosphere on their solar cells. Intelsat was designed to fly at geostationary orbit, where there's no air at all. But down in low Earth orbit, small amounts of atomic oxygen, lone oxygen atoms, would react with the solar cells, causing them to degrade. So Intelsat wanted to stay as high as possible. That was a problem since Endeavour could not get to those altitudes while also carrying heavy payloads. The solution was to meet in the middle, with both spacecraft making their way to an imaginary box in space. Hybrid rendezvous. The Intelsat folks really didn't want to come lower until they absolutely had to. To help ease some of their concerns, STS-49, in addition to carrying Melnick and Akers, also carried a small sample of Intelsat's solar cells. That way engineers could determine just how damaging the atomic oxygen really was to the stranded satellite. The data indicated that they should be fine with a short stay at lower altitudes, but Intelsat still waited until Endeavour had successfully launched before starting to head down. In the meantime, there was plenty of work to do. Endeavour was over-brimming with EVA equipment, including 4 extravehicular mobility units, aka EMUs, aka spacesuits. The crew had to go over every inch of the suits and their complex systems to make sure that everything was in working order. These suits would be slightly different than usual. With 4 spacewalkers spread across 3 EVAs, it might be tricky to tell them apart. So one suit was plain white, another had a red stripe, another had a dashed red stripe, and a fourth had a red stripe with diagonal lines sort of cut out of it. I'm not sure why everything had to be variants of red lines, but sure, why not? The crew also took some time to get some practical experience moving the robot arm around the payload bay. Thornton, Chilton, and especially Melnick all took turns moving the arm through motions similar to what was expected in the days to come. Training never ends. Alright, it's flight day 4, and that distant point of light seems to be getting bigger and bigger, so it seems that we're about to arrive at our destination. I suppose I should tell you all the plan. As Commander Dan Brandenstein eases Endeavour up next to Intelsat, Mission Specialist Pierre Thuet would be perched on the end of the shuttle's robot arm, which will be operated by Mission Specialist Bruce Melnick. At this point, Intelsat's spin will have been reduced from around 10 rotations per minute to a nice gentle 0.6 RPM, but it will still be an imposing presence. A cylinder 3.5 meters across and over 5 meters long, the spacecraft had a mass of over 4,000 kilograms. For Thuet, it'd be sort of like being moved up to the side of a slowly spinning truck. As he was moved around on the robot arm, Thuet would be carrying a carefully designed mechanism called the capture bar. On either side of this bar were clamps that were engineered to grab onto a thin ring at the base of Intelsat, which the satellite manufacturers said was the only safe place to touch the spacecraft. Thuet would position the capture bar over the ring, then push in, causing the clamps on either side to latch onto the ring. If they didn't latch on right away, he could also push a button to force them to engage. Once the capture bar was attached, a status known as soft dock, Thuet would grab a steering wheel-sized ring in the center of the capture bar, called, you guessed it, the steering wheel. With Thuet holding on tight, it was expected that he should be able to stop the satellite's rotation within around 20 seconds. After that, he'd use a power tool to drive some gears in the capture bar, rigidizing it. Hard dock. Next, Thuet would let go of the capture bar, careful not to impart any extra motion. And then he would truly just be along for the ride as Melnick moved the RMS to grab the grapple fixture at the end of the capture bar. It's a pretty clever design. Intelsat had no grapple fixture for the shuttle arm, so they'd use this capture bar with a grapple fixture to grab the satellite, stop it, and then firmly take hold of it with the robot arm. As you recall from last episode, the whole problem with Intelsat was that it was forced to separate from the small rocket that would have pushed it up to geostationary transfer orbit. Since this burn happens at perigee, the low point of the orbit, and it kicks the spacecraft off to geo, it's called a perigee kick motor, or PKM. So Intelsat was stuck in low Earth orbit with no PKM, and thus no way to get to its lofty perch at geo. Well, the STS-49 mission planners had a solution for that. They brought a new PKM. Now, this sort of blows my mind. Normally, integrating a spacecraft with its PKM, or any other upper stage, is a complex procedure done on the ground, probably in a clean room, probably with a whole team of technicians, and probably over a few days. Instead, the plan was to lower Intelsat on top of a new PKM sitting in Endeavour's payload bay, with 2 guys in spacesuits in just a couple of hours. I'll talk a little more about that when we get to it. Now, if you've been listening to this podcast for a while, I'm going to bet that your spidey sense is tingling a bit here. This entire plan hinges on the ability of Pierre Thuot to use this special capture bar to grab onto Intelsat so that he can stop it from spinning and then move it around. We've seen this before. On STS-41C with the Solar Maximum mission, on STS-51A with West Star 6 and Palapa B2, and on STS-51I with LeeSat 3. While ultimately successful, none of those missions went super smoothly, with most carrying a specialized device to capture the satellite that didn't work at all, requiring frantic improvisation. So that's why, as one contemporary space magazine put it, quote, NASA and Intelsat have gone to great lengths to avoid the problems that plagued earlier satellite rescues when equipment designed to be attached to retrieve satellites often did not fit, end quote. All of that preparation and testing paid off when on flight day 4, Thuot reached out, touched the capture bar to Intelsat, and it slowly began tumbling away from him. Wait, what? Yeah, it happened again. The second Thuot touched the capture bar to the satellite, it began to slowly wobble and drift away. With Melnick moving the arm to chase the spacecraft, Thuot tried again, and it just got worse. As the capture attempt unfolded, it was complicated by the fact that the RMS was being asked to move in ways it was not designed to move due to the unexpected new trajectory of Intelsat. After several attempts, the satellite was wobbling too much for capture to be feasible, so they had no choice but to back away. Which was also complicated by the fact that now they had a 4,000 kilogram satellite spinning and wobbling in an unpredictable way right next to the space shuttle. At one point, Mission Control called up a separation burn, and with only 15 seconds to spare, mission specialist Rick Heeb in the payload bay called out that the burn would blast Intelsat with the orbiter's thrusters, making the spin even worse, so they quickly canceled the burn. Eventually, they were able to carefully back away, but the crew was sure that they had just doomed this satellite, which cost $250 million in 2020 money. It was not a great feeling. No one was quite sure what had happened, but it was clear that the dynamics of the satellite and capture bar were not at all what was expected. As Endeavour backed away, the crew and controllers on the ground got to work planning a second attempt, while Intelsat operators got to work recovering control of the satellite. The next day, Intelsat was spinning in a nice predictable way again, Endeavour was back, and Thuot and Heeb were back in the payload bay, ready to try again. This time, the capture was planned in daylight to enhance visibility both for Thuot and for ground controllers watching the video feed. Thuot also practiced the capture several times by pressing the capture bar up against the sill of the shuttle's payload bay. Melnick raised Thuot up, he pressed the capture bar onto the spacecraft, but still, no dice. At one point they thought they had it since the satellite's spin started to slow down, but the capture bar soon came loose and to everyone's surprise the satellite spun back up. It turns out one aspect of the satellite's dynamics that had not been considered was the sloshing of liquid propellant on board. Thuot had momentarily slowed the satellite, but then the propellant sloshed around and kept the angular momentum going. The crew tried for around 3 hours, making contact several times, but burning a lot of propellant trying to keep up with the satellite after each bump. This clearly wasn't working. The crew came back inside. It may not always look it, but EVAs are really hard work, especially for your hands. So with a nearly 4-hour EVA the day before, and 5.5 hours today, Commander Brandenstein recommended a day off. The day off would give the EVA crew a chance to rest up, and give everyone a chance to rethink the plan again. This mission had already performed 2 rendezvous, not to mention station keeping with Intelsat while Pierre Thuot batted it around, so normally we'd be coming close to our fuel margins at this point. The issue was that while there was plenty of fuel for the thrusters on board, there was a pretty limited supply in the forward RCS module, which housed the small thrusters in the nose of the orbiter. The FRCS had to be self-contained. There were no pipes to carry extra propellant from the big tanks in the OMS pods forward to the nose. So if the FRCS ran out, they were done, no matter how much they had in the back. But this flight carried a special piece of software called Payload Bay, which helped the commander deal with relative motion, which helped keep fuel usage down. How? Well, as we've discussed a few times in the past, the relative motion of two spacecraft in a low Earth orbit is not very intuitive. It's not very easy to look at the situation in front of you and predict what it will be in a few minutes' time. In the past, crews have gotten around this by rigidly sticking to rendezvous trajectories that have been prepared and exhaustively tested on the ground. By creating a clever approach profile, you can make things a little more predictable and make maneuvers a little more tolerant of inevitable small errors. But it also means that you have to frequently correct those errors, burning extra propellant. As you may have noticed, we've been getting pretty creative with our rendezvous lately, so crews could definitely benefit from a little more help. The confusingly named Payload Bay Program, written by STS-49 crew member Rick Heeb, ran on a laptop on the flight deck, rather than on the shuttle computers themselves. This made it easier to program, less onerous to update, and the crew could move it around to where they needed it. On the laptop screen, the crew could see graphics depicting the shuttle and their target spacecraft, as well as a series of little numbers tracing out a curve. Those numbers represented where the target would be relative to the shuttle in 1 minute, 2 minutes, 3 minutes, whatever number you were on. That alone is pretty useful, but it didn't stop there. Payload Bay also displayed the relative position and velocity of the two spacecraft, the estimated time to the next maneuver, and some other handy information. It was a one-screen solution that contained everything a rendezvousing astronaut could need. It did this by ingesting data from a few different sources. One was handheld laser rangefinders operated by the crew, simply pointing them up through the window at the target spacecraft, similar to a cop on the highway with a speed gun. Another was the angles of the TV cameras in the payload bay pointing at the spacecraft. By pointing a camera at the target, looking at the angles on the camera's gimbals, and doing some trigonometry, you could figure out how far away that target was. The Payload Bay software couldn't reliably track targets further than 200 feet away, but that was fine since the rendezvous radar couldn't reliably track them once they were within 400 feet, so it was a perfect complement. By using this innovative software, Commander Brandenstein was able to use 15 to 20% less propellant than allotted, making further attempts possible. On Flight Day 6, while the EVA crew recovered, people on the ground and on orbit put their heads together to think of a solution to the capture problem. Eventually, the solution came from the crew themselves. Sketched out on a piece of paper and transmitted down to the ground using one of their fancy new digital cameras, the plan called for the EVA crew to go back outside and assemble a support platform using some convenient struts that happened to be on board. The struts were there for an experiment dedicated to testing more space station construction techniques, but they would work perfectly for their new plan. The platform would allow both Heeb and Thuet to manually grab onto the bottom of the rotating spacecraft by hand at the same time. It turned out that while the spacecraft manufacturer had strongly preferred that Intelsat only be handled by the ring at the bottom, there were a couple other places to potentially grab on. The only thing was, there were 3 of these potential handholds, evenly spaced around the circular base of the satellite. So what the crew proposed was the first ever 3-person spacewalk. The ground was intrigued, but a little skeptical at first. Could 3 spacesuits even fit into the airlock at the same time? The crew had tried it, and with a little jostling and some effort, it could indeed be done. After everyone had mulled it over, the plan was approved. But first we have to get back to Intelsat. Endeavour began its approach with no problems, but when they were about 15 kilometers behind the satellite, the orbiter's computer started to throw errors. To explain this error, let's take a quick, extremely oversimplified look at how computers figure out how to perform a rendezvous. Centuries ago, people figured out some of the basic laws of physics. Decades ago, people took those basic laws of physics and built the mathematical framework to think about this rendezvous problem and make it approachable at all. While the shuttle was being built, programmers working on its software wrote code that could understand that rendezvous math and run the numbers for the crews. Then, during the flight, the crew would essentially ask the computer, "I'd like to know how big the next burn needs to be, please. I'm planning on doing it in 20 minutes, and this is where I'm trying to go." The crew and everyone else already knew that this was possible since it had been planned out on the ground. But when you're really up there, things are going to be slightly different than planned. So the computer has to figure out the slightly different number to use in this specific situation at this specific time. The computer is given a pretty good guess about what the answer should be, so it tries that, sees how it goes, tries another guess and sees how that goes, and keeps trying until it settles in on the final answer. It's sort of like how if you were firing a bow and arrow at a target, you might try firing from one angle, see where the arrow lands, try firing at another angle, see where that one lands, and then realize, oh hey, the target's somewhere in the middle here. That's basically what the computer's doing. But what's critically important here is that the technique the computer is using must converge. That is, if everything is working properly, each guess should get closer and closer until they've got an answer that's close enough to use. And this should happen after only a handful of guesses. Instead, as Endeavour was approaching a large burn that would prepare the final approach, its computer said, hey, I tried this a lot and I just can't make it work. I don't know. And it gave up. Well, what it really said was target iter item 28 exec, but that's what it meant. This is very bad. If this transition initiation burn could not be calculated, Endeavour would just sail right on past Intelsat, and that would be the end of this mission. It was also really scary, since as bad as missing this burn would be, the computer did other things that were way more important. Things like keeping the crew alive. So was this a problem with calculating a burn, or with the entire computer? The crew tried reloading the software, thinking that maybe the computer just gotten itself mixed up, but nope, same result. With the burn coming up soon, a decision had to be made, fast. They could either bail out of this entire approach and attempt a fourth rendezvous later, or they could perform a small burn planned on the ground that would buy them 90 more minutes to think about what to do. They did not have the fuel to do both. So, after some quick discussion, with only 2 minutes to go, the decision was made to perform the small burn, delay everything by an orbit, and take the extra hour and a half to closely look at the situation. The remaining maneuvers could be calculated from the ground and read up to the crew, but it was important to make sure that the computer was working well enough to perform the approach safely. Finally, the crew were given the green light, and they moved in for the last part of the rendezvous. This isn't going to be the most satisfying explanation, but just so I don't leave you wondering, the issue with the rendezvous code was later traced back to just one function used to perform what's called Lambert targeting. I've gone deep enough into the weeds on this episode, but for the computer science-minded among you, the problem was they had mixed single and double precision floating point numbers. Bad idea. This code had already been used multiple times on this flight and had no issues, but under just the right circumstances, it could fail. While Commander Brandenstein brought Endeavour in, Thuet, Hebe, and Akers finally left the airlock. After being stuffed in there for an extra hour and a half, I'm sure they were relieved to get some fresh air, or some fresh vacuum. Before they could attempt to capture the satellite, they took out a bunch of the struts for the space station EVA experiment and built a platform across the width of the payload bay. With Hebe attached to the payload bay sill, Akers on the platform, and Thuet on the RMS, they could form a triangle around the satellite. Brandenstein very slowly and very carefully brought Endeavour in closer, such that the satellite descended down between the three spacewalkers. For 15 minutes, they did nothing but just watch it, to make sure that they fully understood its motion, and to wait for the slight wobble to line up the way they wanted. Finally, Thuet called out, wait, let's do it, and all three men grabbed on at once. Intelsat immediately stopped. After a moment, Brandenstein called down, Houston, I think we've got a satellite. Just to be certain, they maintained their firm grip for over half an hour to make completely sure that everything was settled. They didn't want to let go and have sloshing fuel spin the thing up again. But at long last, it seemed that they finally had things under control. In an operation made slightly more difficult by being further down in the payload bay than planned, Thuet scooted underneath the spacecraft to attach the capture bar. The bar was still needed in order for the RMS to grab onto it, and it was actually how it would be attached to the perigee kick motor. After all that work and after all those attempts, once they actually had hold of Intelsat, the rest of the EVA went extremely smoothly. The crew had no trouble lowering it down onto the PKM, clamping a few latches onto it, and connecting a few wires. As is typical with these satellite rescue missions, once they had control of the spacecraft, they could fall back on their excellent training, and everything was a piece of cake. Well, mostly. Before deploying Intelsat back into space, The 3 EVA crew piled back into the airlock just to be safe. Kathy Thornton flipped the switch and nothing. She flipped the backup switch and nothing. It seemed that now that Intelsat had finally connected with Endeavour, it didn't want to leave. The problem was eventually traced back to a minor wiring difference between Endeavour and the other orbiters. The problem wasn't with the hardware, it was with the procedure, which had not been updated. Though I will say, as I recently learned from someone with first-hand knowledge of this particular deploy mechanism, the wiring on the mechanism itself wasn't the most intuitive either. You'll hear all about that a few flights from now. Within a few minutes, Mission Control instructed the crew on how to reconfigure things, and finally, the repaired Intelsat was sent on its way. Just goes to show why it was so important to make Endeavour as similar as possible to the existing orbiters. Intelsat went on to successfully reach geostationary orbit, where it enjoyed a long and successful career spanning decades. The EVA crew cleaned up a bit and headed back into the airlock again, their job complete. Their spacewalk had lasted 8 hours and 29 minutes, breaking the 20-year record set all the way back on Apollo 17, and it would stand for another 9 years. And as of 2020, it remains the only 3-person EVA in history. Unfortunately, both then and now, the extra time spent on the Intelsat rescue meant that less was available for the next major experiment of this flight: assembly of space station by EVA methods, or ASEM. What was originally supposed to be 2 EVAs was quickly replanned to take only 1. And since I just spent a long time on Intelsat and still have some more stuff after this, I'm going to keep this section a little short. ASEM, from what I can tell, is more or less a carbon copy of some earlier EVA evaluations. Kathy Thornton and Tom Akers headed outside and assembled some structures out of special metal beams. They weren't really planning to use these beams on the space station anymore, but practicing building it in space and moving around on them would be valuable. They next moved some heavy things around the payload bay just to see how easy they were to control. This bit was important, since the space station was being designed with replaceable modules that should be easy for spacewalkers to swap out, but they would have a considerable mass. There was also originally a plan for the RMS to take the spacewalkers out over the nose of the orbiter, where they'd try some similar tasks, but without the lights and thermal environment provided by the payload bay. But this was scrapped for time. The crew found that while they were firmly anchored in the payload bay, building stuff was super easy. But when they had to climb up on the structure, it was really difficult, since there was nothing for them to push against. But I think Gene Cernan, way back on Gemini 9A, could have told them that. Thornton and Akers also tested a couple of devices designed to help rescue crew members who drifted away from the structure. With the space shuttle, if someone drifted away, the shuttle could just go get them. But with the space station, that was going to be trouble. These devices included an air gun, sort of similar to what Ed White used on Gemini 4, an extendable pole, or my favorite, literally just a rope that they would throw back to the structure and try to lasso something. Taking that space cowboy thing a little literally. After a considerably more dramatic than planned but still successful mission, Endeavour safely touched down for the first time at Edwards Air Force Base. Pilot Chilton deployed the new drag parachute, which quickly inflated behind the new orbiter, helping to slow the vehicle and stabilize steering. The wheels stopped, and the 8-day, 21-hour, 17-minute, and 39-second mission was in the books. So, I think we can take some lessons learned from this mission. For one thing, if there was any doubt, there isn't now. The EVA training program was insufficient for the jobs being asked of the crews. Don't get me wrong, NASA is great at training. They probably have the best trainers in the world. And the training was incredibly good at familiarizing the astronauts with the equipment and the procedures. Astronauts know those suits inside and out. They could handle contingencies, they could operate all the tools, they could do tons of stuff and do it super well. But the training was completely failing to accurately replicate the dynamics of things in space, which is a lot to ask because there's gravity on Earth. Everyone had been surprised by how sensitive Intelsat was to touch, immediately wobbling and moving away from through it. While Thornton and Akers climbed around on top of the ASEM structure, they struggled with their movement. Akers could even be seen kicking his feet instinctively. What was different? On the ground, the crews trained in a big pool. When you push something underwater, the water stops it. When you kick your feet in water, the water pushes back. In space, when you touch something, it just keeps going. When you kick your feet, Nothing happens. Even using a second major training facility, which was basically a giant air hockey table with a nearly frictionless surface, they could not accurately replicate the weightless environment. The Intelsat stand-in might get pushed around, but since it was firmly on the floor, it couldn't wobble. I don't know all the repercussions of this flight's EVA experience, but I do know that it was a strong bit of feedback for both trainers and mission planners. They either needed to come up with some exceedingly clever training strategies, or simply accept that, maybe this particular type of capture mission is not a thing that we can do that easily. Maybe we should plan our missions around that knowledge. Which leads me into my next result from this flight. STS-49 was an undeniably exciting mission. Grabbing a satellite and strapping a new rocket to it is like something out of a movie. And while it's stressful and dangerous, clever and improvised spacewalks are interesting and thrilling. It's why I spent so long talking about it. Newly appointed NASA Administrator Dan Golden even said the flight has, quote, brought the magic back to the space program. But he also appointed a panel of experts, including Apollo astronaut Tom Stafford, to take a look at the entire concept of satellite rescue and how we should be thinking about it going forward. Adjusted for inflation to 2020, the flight cost around $660 million. And in addition to the inherent risk of flying in space, the crew was doing some pretty risky operations in close proximity to a satellite. The satellite operators paid NASA $175 million. So you gotta ask, did NASA get $485 million worth of results out of this mission? Yes, they learned how to do some interesting and difficult EVA techniques, but did they apply to anything but this type of mission? Yes, it got 4 crew members more valuable EVA time, which would come in handy when repairing Hubble or building the station. But could they have been doing something more useful to NASA than banging on the side of Intelsat? There's also public image to be considered. I, like many of you I'm sure, find the idea of considering public image to be somewhat distasteful, but the reality is that it does matter. Showing off in front of the world that America is a country that can do this kind of thing, and that NASA can get this difficult task done, is worth something, but it cuts both ways. Even if no harm came to the crew, if they were unable to capture Intelsat, it's likely that the negative PR would have greatly outweighed the positive PR of a successful mission. And lastly, let's consider the value of simply having this ability at all. Forget about public image, forget about cost. What if there was a payload of critical national importance that could only be rescued by the shuttle? As detailed by the panel's report, this was actually somewhat unlikely. How many satellites launch every year? How many launch into orbital inclinations reachable by the shuttle? How many of them have a parking orbit at all, which would give it a chance to be stranded in a low shuttle-capable orbit? And of those, how many suffer a problem that's even possible to fix by astronauts, who are extremely skilled, but limited by bulky gloves and the tools available? When you run the numbers, it turns out that this was actually not a super common scenario. It was for all of these reasons that this type of rescue mission is now firmly in the rearview mirror, even if intricate and exciting EVAs like Hubble repair remain ahead. The space nerd enthusiast in me is slightly disappointed by this, since who doesn't enjoy the thought of bold and daring space rescue missions? But when I sat back and considered the panel's findings a bit, I found myself agreeing. NASA should play to its strengths. It should build satellites with repair in mind in the first place. And it shouldn't take big risks with space shuttles and crews to bail out companies that probably should have just bought the launch insurance in the first place. Still a really cool mission, though. Next time, Columbia has Space Lab back in the Payload Bay, and it's in it for the long haul. Continuing to ramp up shuttle mission duration, Columbia will be flying around the Earth for almost the same amount of time that I make you wait between episodes. Ad Astra. Catch you on the next pass.